Hello everyone. So today we want to do our third video on the Terrell Penrose Effect, which, as you may recall, has to do with the deformation in the shape of rapidly, which is to say relativistically moving objects. So in the first talk, we gave a visual introduction where we showed some of the interesting deformations that you can get in simulations. And in the second video, we did the mathematics that underlies the simulations. And today what we want to do is a special case, which is the case of purely radial motion. The advantage of this particular case is that it is analytically solvable and leads to some rather interesting physics. So let's remind ourselves what this was all about. In the case of let's just start with a review first of all. Here's a review. Let's say we have an observer down here. Here's our observer. He's at the origin of a set of coordinates, x, y, z. And out here let's start with a single point source. We have a single point source of light moving at a velocity v. Okay? So, at a certain time, this object, this point source, emits a ray of light, and this ray of light makes its way to the observer. And at the point that it reaches the observer, the point source has moved to here. It's kind of like the Zeno's paradox, the Achilles and the tortoise and the hare. So by the time he gets here, the ray of light is here. So this is over here is what we would call the true position of the object. And this is what we would call the apparent position. And the idea is that because the speed of light, this thing's moving at velocity c, the speed of light, which we typically take to be 1 for simplicity. Whenever an object is moving at any appreciable velocity relative to light speed, the apparent position and the true position tend to be different, okay? In ordinary life, we don't have to worry about this. The apparent position and the true position of an object are incredibly close to one another, so close that for all practical purposes they are identical, okay? But we worked out an equation for this, which I will remind you of here. We ended up getting something called the latency. Latency is the time it took for the ray to go from here, the point source, to the observer. And what we got was the following equation. We got gamma squared r, the distance between the observer and the point source, and that has a square root of 1 minus v squared plus r dot squared, where r dot is the radial component of the velocity. And that's where this square root ends, minus r dot. So that was an important equation. We also had the equation, once you know tau, the latency or the light travel time, you can also determine r apparent. Sorry, let me do that more cleanly. R apparent is equal to r current, which is this position over here, minus v, which we assume to be constant, times tau. So that's everything you need to know for a single point source, okay? If there are, on the other hand, if there are two or more sources, then you have to bring another equation into it, which is the fact that there's Lorentz contraction involved. We have Lorentz contraction, so let's write this in first of all. Lorentz contraction comes into play. It did not come into play here because you can't contract a point source. But if you have two things, then the distance between them may change depending on which way the thing is moving. So you have Lorentz contraction, which says that the length contracted, let's say, of a thing is equal to L, its rest length, divided by gamma, the same gamma that's up here. And you may recall that gamma is equal to 1 over the square root of 1 minus v squared. Again, this is in natural units. Okay, very good. Okay, so with that review out of the way, let's now address the case for today, which is the case of purely radial motion. Let's put this down here. Okay, so for the case of purely radial motion, things simplify. We have this equation up here for tau. Again, that's the latency, or if you want to call it the propagation time. And in this case, the simplification is that r dot and v are one and the same. Okay? Which is to say the radial velocity and the total velocity are one and the same. So that allows this thing to be simplified. In particular, these two terms cancel, and this whole thing just becomes 1. So we end up with, let's write it here, tau equals gamma squared, r, again, r is the current true position of the object, times 1 minus r dot. Okay? Okay, now we can actually go a step further in the simplification, because gamma here can be written as, so gamma squared, if we square this and use the fact that this is the same as r dot, v is, we can write gamma squared equals 1 over 1 minus r dot squared. And that in turn, this is gamma, not r, by the way, gamma squared equal to 1 over 1 plus r times 1 minus r. Okay? And if we put that in here, put this in here for this gamma squared, we get tau equals r. And now this guy cancels this guy, and you're just left with r over 1 plus r dot. These are supposed to be dots here, by the way. Okay, so that's our simplified equation for tau. Okay, now that we have an expression for tau, let's put this into the equation of motion. Okay, so we're going to get r apparent is equal to r minus r dot tau. That's the one-dimensional version of the equation of motion, where we're using r dot in place of v and r, the scalar, in place of r, the vector. Okay? So this gives us r minus r dot r over 1 plus r dot. And then we can make that, we can put the r out front, and we get 1 minus r dot over 1 plus r dot. Now, let's make this over a common denominator. So we're going to get r outside again. Now we're going to have 1 plus r dot minus r dot over 1 plus r dot. And those r's dots cancel, and you get r over 1 plus r dot. So let's just summarize that here. We'll say r apparent is equal to r over 1 plus r dot. So that's our equation for the apparent distance in terms of the current true distance. So now we have an equation that describes everything you want to know about a single point source moving in a radial direction relative to an observer. Okay? And it involves r, the current true distance to the object, its velocity, r dot, and this gives you the apparent distance to the object. And the apparent distance always lags behind, as you know, the true distance. Okay? So that's the key thing. So let's now grab this. I'm going to grab this equation because we're going to need this again. So I'm going to say copy. Let's now go up here and paste it. So this is the equation of interest, and we want to now use this equation. We want to use this equation for the case of 2-point sources. And the idea of 2-point sources is this. You have an origin of coordinates here. So this is our little XYZ coordinate frame here. And there's an observer here. Okay? And over here is a point source 1, moving with velocity v away. And there's also another point source, 2, also moving with the same velocity v. And actually, sorry, that's wrong. My apologies. We want that to say r dot. And similarly here, this is r dot. Okay. And the distance between them, let's say from here to here, is L. And that's the system that we want to look at. Okay? So now we can say RA1, so this is point source number 1, is equal to R1 divided by 1 plus R dot. No surprises there. We can also say RA2, distance to point 2 apparent, is equal to R1 plus L divided by 1 plus R dot. And so if you subtract these, you get L sub A, the apparent length, which is RA2 minus RA1, is equal to just L over 1 plus R dot. Very good. But now we want to remember that L is, sorry, I'm getting ahead of myself. L is the Lorentz contracted length. So L is equal to L0 divided by gamma, which is again equal to L0 times the square root of 1, minus R dot squared in the notation we're using here. So, okay? So if we put this in here, we get L sub A equals L0, and I'm going to write this in a special way. I'm going to factor this. So it's going to be 1 minus R dot times 1 plus R dot. And we're going to divide this by, and I'm going to square this. That allows me to put the whole thing under a square root. So we're going to have 1 plus R dot squared, and I'll put the whole thing under the square root. And now notice this factor cancels one of these. So we just end up with L sub A let's write that a little more cleanly. No, that's not what we want. Equal to L0 times 1 minus r dot over 1 plus r dot square root. That's the key equation. Okay? Okay, so now let's consider this equation a little bit more carefully. Let's consider what its ramifications are. So let's write it again just for clarity. We have L apparent equals L, which is the rest length of the object, times the square root of 1 minus r dot, the radial velocity, divided by 1 plus r dot. Okay? That's the equation of interest. And the first thing to notice is that it has the same form, interestingly, as the Doppler effect. The Doppler effect. Specifically, the longitudinal relativistic Doppler effect for frequency, just to be really clear, for frequency. So that's an interesting observation. Next, let's consider what happens in two limiting cases. In the first case, we want to say r dot goes to 1, which means the radial velocity is going to the velocity of light, which is 1, and and the source is receding. Okay? And in that case, we see that we get this becomes 1, so we get a 2 here. 1 minus 1 gives 0 here, so we get, for this case, the apparent length is equal to 0. Or to put it differently, let's be more clear about this, it goes to 0 in the limit as the radial velocity goes to the speed of light. And again, this is receding. Now consider the other case, the other extreme. R dot goes to -1. So this is the case where the object is approaching the observer. And in this case, what do we get? So let's think about that. The denominator goes to 0. So that's interesting. While this becomes 1 minus -1, so this becomes 2. So basically, the apparent length actually goes to infinity. So this result, let's talk about this result here first. LA goes to 0. So again, this is for the case of a receding source. That is to say, a point source that is moving away from you, the observer, at some very considerable velocity, very near the speed of light. Okay? So the question is, what does this mean? It means that the object appears flattened. It appears flattened. Okay? That's what this is all about. And that does not entirely surprise us because we have, after all, Lorentz contraction going on. On the other hand, we have this result, which seems to fly in the face of Lorentz contraction for the case where the object is approaching us. So let's try to understand what's going on with this apparent length going to infinity. Let's scroll back up here for a moment. Let's remind ourselves of this. Look at this formula right here. This is what we got before we took Lorentz contraction into account. Pretend that this, for a moment, there is no Lorentz contraction and that this is L0. That's not really correct, so I'm going to take it away immediately. But you see you get this 1 plus r dot factor, and in the case of the approaching source, this denominator goes to 0. So this piece is the, let's call it the latency effect. And that effect is what's causing the blow up. On the other hand, you have this equation over here for the Lorentz contraction, and of course this gives us this gives contraction always. So this one never varies in its effect. So you have the Lorentz contraction here, Lorentz contraction, and then you have latency, and they're opposing one another. And what's happening in this case is that the latency effect dominates the Lorentz contraction effect. So quite interesting. Now let's make a couple of other points about all this. We're using the word apparent a lot. The word apparent, let's remind ourselves what we mean by apparent. Apparent has to do with the emission. It's the emission point of the ray that we are currently observing at any given instant. Okay? So apparent, so we have to make the point that apparent is not equal to readily apparent. Just because an object is apparently contracted or extended in this very specialized sense. Let me write this again. I'm not happy with the way this looks. Readily apparent. And the reason for this not equal is that this distortion that we see here, this all occurs along the line of sight. And so for that reason, it is nearly invisible. It's 99%, shall we say, invisible. It's to the naked eye. It will require a rather subtle measurement using some sort of statistical approach, I think, to actually show this effect for a given object or a set of objects.